welcome you all to the day 6 of our faculty development program. We trust that you have found the past sessions enriching and engaging, providing valuable insights, new perspectives, and practical skills to enhance our teaching and research. As we enter the sixth day of this transformative journey, let us keep the momentum going. Today's session are designed to build on what we have covered so far, diving even deeper into advanced topics and innovative methodologies. Our esteemed speakers are here to share their experience and guidance through the another day of inspiring learning and collaboration. Thank you for your active participation and enthusiasm. Let us make the most of day 6 as we continue to learn, connect, and grow together. Before we move on to the session, here is today's guest, Dr. G. Muralidharan, Professor of Physics and the Chief Vigilance Officer at the Gandhigram Rural Institute. Dr. Muralidharan has made a lasting impact through a career spanning over 40 years of research and 35 years of teaching experience. His journey through academia reflects a commitment to pushing scientific boundaries and a dedication to nurturing future generations of physicists. Dr. Muralidharan's academic journey begins with a master's in physics from Madurai Kamaraja University, where he developed a keen interest in material science. Pursuing this passion, he have completed his PhD from prestigious Indian Institute of Technology, IIT Madras. This strong academic foundation paved the way for his future research, leading him to the specialize in several critical areas within the physics. Throughout his career, Dr. Muralidharan has carved out a niche in several high-impact research areas, which includes thin film devices, nanomaterial-based devices, instrumentation, and material chemistry. Dr. Muralidharan's dedication to student mentorship is equally impressive. Over his career, he has guided 32 students in their academic journey, including 17 PhD scholars and 15 MPhil candidates, with 2 doctoral students currently working under his supervision. Many of his mentees have gone on to establish their own successful careers in their academics and industries. Dr. Muralidharan has an extensive publication record that speaks to his active engagement in research and his dedication to knowledge. He has authored 160 journal articles which reflect the quality and the impact of research in physics and material science. Additionally, he has presented at 158 conferences, sharing his findings with an international audience and contributing to the global exchange. His recorded video lectures, in total 20, has produced a part of UGC program and broadcast on Doordarshan's Dhyan Darshan channel, extend his reach, making his insight accessible to a broad audience of learners and enthusiasts. In addition to his research and teaching role, Dr. Muralidharan has served as a valued member of the editorial board of several academic journals. He also frequently acts as a referee for prestigious journals, such those published by the Royal Society of Chemistry, the American Chemical Society, Journal of Physics and Chemistry of Solid, and Material Research Bulletin. His contributions as an editor and the peer reviewer help to maintain the quality and rigor of academic publications, ensuring that not only high quality research reaches the scientific community. Dr. Muralidharan has played an instrumental role in the administration of Gandhigram Rural Institute, taking on the various leadership positions that underscore his dedication to fostering the academic growth and institutional integrity. His current administrative role includes Chief Vigilance Officer, Special Officer, Sponsored Project and Action Research Cell, Director, University Scientific Instrumentation Center, Coordinator, LRM Lamp Nodal Center, Head, the Department of Physics, Dean, School of Science, and last but not the least, Registered in Charge and Director of Academics. Dr. Muralidharan's commitment to academic goes beyond his own research and teaching. He has organized 3 UGC-sponsored reference courses and 3 national-level conferences, helping to facilitate the exchange of ideas, knowledge, and best practice among the students, researchers, and industry professionals. Dr. Muralidharan's career in a testament to his relentless pursuit of excellence in physics and his dedication to the academy has made a marvelous change. His pioneering research, impactful teaching, and comprehensive leadership role reflects his holistic approach to education and research. Through his mentorship, publication, and service, Dr. Muralidharan continues to influence and inspire the next generation of scientists contributing to the advancement of knowledge and innovation in physics and material science. I am truly honored to welcome such an eminent speaker who has joined us with today to share this knowledge. We welcome you, sir.
Thank you. Thank you. Shall we start?
Yes,
Hello?
sir.
Yeah.
Yes, sir. We will.
So, we'll start. So thank you, Dr. Uma. I'm very happy that Dr. Dhanush of the chemistry department and other friends for suggesting my name for this FDP. I was told this FDP was to be hosted by AICTE, but now the college has taken up the honors of doing it. I'm extremely happy to be part of this. Initially, I was very hesitant to take this because the title was more on quantum computing and all that. Finally, I could see one small slot wherein I can fit in, which is on quantum materials and devices. Today's talk, I'll be concentrating on this quantum materials and devices. First half of the lecture will be mostly on quantum materials, their preparation, characterization, and in the second half, I'll try to give you a glimpse of how to use quantum materials for making devices. Yeah, I think people can see the slide. So is the slide visible to you?
Yes, sir. Yes, sir. It's visible.
Yeah. So this is the basic title of the talk, quantum materials and devices. The first question that normally comes to our mind is, what are quantum materials? We know about the materials. When you look at probably a big chunk of rock, whether it is 10 meter by 10 meter by 10 meter, or it is only 1 centimeter by 1 centimeter, or 1 millimeter by 1 millimeter, the physical properties of sand or this rock is not going to be any different. But you see that when the size is reduced from millimeter to micrometer to nanometer, things change a lot. The material doesn't behave the same way when the size is reduced to a very large extent, something like having 100 nanometer size in any one of the dimensions, a very small dimension. At this dimension, what really happens is the properties cannot be described by either the classical physics that we have learned or the semi-classical physics we have learned. Rather, the properties are more controlled by the quantum interactions that are taking place in these materials. This can be easily understood using some simple ideas. Let's look at a normal material, maybe a spherical material. You will see that the number of atoms sitting on the edges will be given by 1 by R, number of atoms sitting and the number of or the ratio of surface area to volume is something very different. If you take it to be either a cubic material or a squarish thing, you'll see that it depends on 1 by r size. When the dimension decreases, when r decreases, the increase is very large. When you go from millimeter to micrometer, it goes by 10 power 3. When you go to nanometer, it goes by 10 power 6, and all that. You see that the surface available for any reaction is going to be very large. Now, let's look at another interesting thing. If you are in a sea of people, number of people surrounding you is very large. Let's now say that there are only 5 people, 4 of whom are sitting on the corners of a square, and the 5th one is sitting at the center of the square. You see that of the 5 people sitting in that square, 4 are on the outer side. Only one who is sitting in the middle will be connected to all the other 4, whereas the other 4 who are sitting on the edges are not fully connected. At the edges, they are free. This exactly is the case when you look at a nanomaterial. The material itself is very thin, very small, and you see that large amount, even about 50 to 60% of the material is on the surface. Whatever material is inside, the atoms that are inside the material are going to see almost a similar environment. When you come to the top surface, you see that the top surface, the atoms are not connected. When I say connected, it is connected probably at the bottom, it is connected on the sides, but on the top, if you see, the atom is not connected to anywhere, it is only a vacuum. When I say vacuum, please do not get confused with the absence of air, absence of gas molecules. It is where the similar kind of atoms are not present above this particular level, and as a result of which they become completely different in property. The behavior is governed by quantum mechanics or the quantum physics, and you see that the electrons become strongly correlated. Electrons interact with electrons. That's how you get superconductivity, where 3 physicists, Cooper, Schrieffer, right? And these 3, Bodin, Cooper, and Schrieffer, proposed the theory that the electrons interact through the lattice with another electron. So instead of a single electron movement in superconductivity, you have electrons coupled. Coupled electrons are moving. It is something like 2 electrons moving together. You see a great thing wherein the scattering is not there. The electrical conduction has been enormously improved. That is only because of the strong electronic correlation. Then comes to magnetism. When you go to magnetism, we'll say magnetism is due to magnetic dipoles. If currents are flowing, we get dipoles. Normally in a material, these dipoles are oriented in random directions. When the dipoles are oriented in random directions, all that you see is the net dipole moment is 0. But by applying an external magnetic field, you will be able to align these magnetic dipoles in a single direction, by means of which the dipole moment will be strengthened. You get a net dipole moment in a particular direction. That is known as paramagnetism. Where the magnetism is large, the material gets attracted to a magnet. But when the size of the material is so much reduced, the alignment becomes so strong that these dipoles interact very well, and the magnetism is multiplied manifold, leading to what we normally call as a super paramagnetism. The other thing is, so far people have been using only certain properties like the electronic energy levels, vibrational energy levels, and other things of electrons for making devices. But today, scientists have been working on using the spin of an electron for applications, and this science is known as spintronics. Using spintronics, people are trying to make quantum devices. The gates that we are talking about, the AND, are not, and other gates, and even devices people are trying to make, but still, unfortunately, it has not been realized fully. Only few basic gates could be realized so far. I do believe that in the years to come, probably in another decade or two, the quantum computers would appear at least in the laboratory, and probably in another 2-3 decades, quantum computers become a reality wherein the amount of energy spent, the speed at which you process, everything will undergo a very big shift for the good. And this, I told you earlier, materials whose dimensions are in the nanometrology, they show a behavior very different. I'll try to give you a glimpse of how the properties are altered when the materials are in a very, very small size called mesoscopic or nanometric scale. The grain sizes. What I mean by grain is, if you take a rock, powder it, you get sand. If you look at it, each speck of the sand is what you call as a grain. So similarly, in the case of nanomaterials or the quantum materials, the grain sizes are about 50 to 100 nanometer, a very small size. And as I told you, the surface to volume ratio, if you look at it, it is something like, for a sphere, it is 4 pi r square over 4 by 3 pi r cube. You know that it's approximately 1 over r. For if you reduce the size by 1/10, the surface area increases by a factor of 10. You see that the large surface is there. So these materials are very useful when the surface properties of materials are our concern. For example, when people are interested in removal of dye from wastewater, there are many methods by which the dye can be removed. One of the methods will be to have a pond, slowly evaporate it, then you have the dye in a sort of solid form which can be removed. But the efficiency of dye removal by evaporation method is very poor. That doesn't do it. So what normally people do is they try to use materials that absorb the dye. I would repeat that, absorb the dye, or the dye gets connected and attached to the surface. When the dye gets attached to the surface, the dye is removed from the wastewater, and thereby the waste is treated, and we'll have a waste which is not dangerous for human consumption. And then again, as I told you, the grain and grain boundaries. What do you mean by grain boundary? If you have a particle like this, then I'll have another particle like this. This is known as the grain boundary. These grain boundaries and all that are very essential. They scatter and do it, and because of the small grain size, you'll be able to do a lot of things. For example, if it is a bulk, there are phenomena where charges are to diffuse into the grain. When the grain size is large, the diffusion will happen only in the first few layers, and you don't have good diffusion. Rather, if you make the size to be very small, of the order of about 50 to 60 nanometer, the charges can easily get into it or diffuse into it easily, and you see that diffusion is very, very effective. Again, I told you about atoms staying on the boundaries. You can see that if you make a particle of 5 nanometer grain size, about 50% of the atoms are on the boundaries. On the boundaries, that means they are very reactive. We may ask, sir, is it always advantageous that all the atoms are sitting on the edges? The answer is certainly not yes. They are not advantageous because all these atoms are sitting on the edges. They are so reactive that when you make a material of average grain size 5 nanometer, prepare it today, measure the dimensions, and keep it stored for about a month, measure the dimensions, store it for 6 months, measure the dimensions. You will see that progressively the dimensions will increase. It may go from 5 nanometer to 10 nanometer when you store it for 6 months. That's because of this strong reactivity. They join together. Normally in scientific terms, we call it as agglomeration or aggregation. You see that the aggregation happens, and because of the aggregation, you see that size changes. Then comes a question, sir, can we stop this aggregation? Right? Naturally, we ask the question, if the quantum material is prepared, a bare material is prepared, and if this material is not going to be true to itself but keeps on changing with time, how do I work with it? If I buy rice, for example, whether I store it for 1 month, 1 week, or 1 year, rice has to remain as rice. And as rice keeps on changing its properties, how do we use it? So naturally, there is a need for arresting the aggregation. People use a very simple technique known as capping. People use a technique known as capping. Don't get I think there's nothing great about capping. All that we do in capping is, it is something like trying to make the potato vada or bonda as we call it. You make the potato balls, soak them in the dough and deep fry it. When you do that, you see that the surface that is available for you to see is only the dough, kadala mavuda. It doesn't go up to the inner thing. So all that you do is the material is capped so that the bonds which are not completed will now be pacified. They are not that violent. The bonds are pacified, but still I have a material whose grain size is only 5 nanometer, for example. And the properties depend on the grain size. What do you mean by properties depend on grain size? You will see that the band gap, in case you make a semiconductor with maybe a compound semiconductor or a elemental semiconductor like silicon or germanium, their band gap changes. For bulk, we say that silicon has got a band gap of 1.4 electron volt, but you'll see that when you make it in the dimensions of nanometer, the band gap would increase. It will not be 1.4, it can be 1.6, 1.7. So the band gap changes with that. The electron energies are altered. I told you they are not electrons that you see in a solid, because in a solid it is a sea of electrons. They all interact and you have a lot of problems like scattering of the electrons. Electrons undergo various kinds of reactions. But whereas in the nanometer regime, the electrons interact so well that the quantum mechanical behavior is totally altered. And because of that, you see that the band gap is altered, their energies are altered. As a result, the absorption of radiation will be altered. Not only that, the strength increases. When you make carbon as a carbon nanotube, its strength is far superior to the best steel available today. It is thousands of times stronger than the best steel available. You see that the strength increases to a larger extent. So is the case of hardness, hardness increases. Then, because of the small size, the diffusivity, the ease with which atoms, ions, or charges can enter into a material is enhanced to a larger extent, and solubility is also increased. Higher electrical, I'm sorry, there is a mistake. Higher electrical conductivity is not resistivity. Higher electrical conductivity is there, and you have enormous applications. So before I proceed further, I would like to inform the audience that you can stop me at any point. I'll clarify your doubts if any, and then proceed. So now you see a very interesting picture wherein you see that I have four types of silver spheres and two types of gold spheres. You look at the size. When I have silver in the 40 nanometer size, it appears bluish in color. You try to make it a 120 nanometer appears whitish, and you make it in 100 nanometer reddish in color. Similarly, when you make gold with 50 nanometer, it is greenish in color. And the same thing when you make it in 100 nanometer, it is orangish in color. You see that the size variation leads to change in color. And this has been enormously utilized by our ancestors to make glass panes. People who would have visited some of the old temples, and in case you visit some churches, you'll see that the glass panes will have different colors. They never used pigments like what we use today. They were using nanomaterials without knowing that these are nanomaterials that provide you different colors. And what all things you can do? You can have passive nanostructures which can be dispersed. Then the products that incorporate nanostructures like coatings and other things which permit you to get a variety of materials, you can make ceramics. What is a ceramic? If you have a glass and part of the glass can be crystallized, you call it a ceramic. So into a ceramic, if you introduce crystals of nanostructures, then it becomes a ceramic whose strength is enormously large and is useful. You can make active nanostructures which are bioactive. So maybe we tend to ask a question, what is bioactive? See, when normally a drug is given, the drug flows in our bloodstream, keeps on flowing, and it is utilized only by one particular organ which needs the drug, and otherwise major portion of the drug is wasted. That's why doctors used to say when you take antibiotics, eat or drink lot of water, so that all the antibiotic that is used, that is not used by the body, will be washed away in the urine. So you can have bioactive nanostructures and use them in what are known as targeted devices. Targeted drug. What is a targeted drug? People have identified that if you want to treat the gland, thyroid absorbs iodine. So what people do is that they try to attach the drug to iodine and deliver it so that whatever drug you are sending it to cure the thyroid, that this iodine will go and get attached to thyroid, and thyroid gland will be receiving the drug and not any other part of thing. That way you are able to specifically deliver the drug to a particular location which really needs it. You see that the efficiency is very large. Probably instead of the doctor giving you 1 gram of the medicine, he may give only 1 milligram of the medicine, and maybe even a smaller quantum, so that the toxicity of the medicine is not large. Similarly, you can have 3D transistors, amplifiers, actuators, everything. Things become so small. People talk about MEMS, micro electromechanical systems. Now you can have nano mechanical, electromechanical systems. There are structures that can adopt and all that. You have guided assembling. You can guided assembly can be done. You can do robotics at a small scale, something of the size of a micron, which will be able to get into the body and analyze the thing. You can also have a molecular device by design. There are a number of chemists, physicists, and biologists working on devices and computing systems, and they try to devise molecules with specific curative ability. The curative ability is decided, molecules are designed. Now you have molecule design mechanisms. You can easily do a simulation. But now comes a question. So I've been talking mostly about sort of advantages, what really happens, this, that, and all that. There is also a very big problem that handling of these quantum materials or the nanostructures is equally difficult, because if they are let into the air, they can easily penetrate into the human body and cause. So one has to take enormous care in preparation and handling of these materials. So let's look at a case where the material has been shredded into nano dimensions, and what really happens to the melting point. You see that when you make cadmium selenide, if it is a bulk cadmium selenide, when I say bulk, it can be a millimeter by millimeter. It melts only at 1678 Kelvin, or say about 1400 degrees centigrade. And the moment you make it into a 3 nanometer cadmium selenide crystal, it melts at 400 degrees centigrade. You see the thing. This is why we say the quantum materials are very interesting for us. From 400 degrees centigrade, from 1400 degrees centigrade, we are able to go to 400 degrees centigrade. That's a great thing. You will be able to modify the melting temperatures, and you can use it for analyzing the material. You just look at it, what is happening when the size is about 100 nanometer, when the radius is 50, I'll say 100, it melts at 1400 Kelvin or maybe 1100 degree centigrade, and as you reduce it and bring it to about 10 nanometer size, the melting point is only 400 Kelvin. It's a very small thing, and you can use it to your advantage. Similarly, what really happens to the particle? I told you, if you store it for longer, the size increases. Now comes the question. What really happens when you heat them? When you heat them again, the heating will lead to increase in size, because they try to attach to each other and they grow in size. You can see that the material, which was about 10 nanometer in size, right, at room temperature has become 40 nanometer at 300 degrees centigrade, and about 180 nanometer at 450 degrees centigrade. That means one has to be very careful in storing them at different temperatures. It's very essential that we understand this, but please try to understand this would happen only for materials which are not capped. If the nanomaterial is capped, then there is no question of aggregation, either due to storage or due to heating. It cannot happen. I'll go back to what is this capping. I told you, you can do it. It is something like you are making, I think, padusha. Padusha is something you make a round material, put it into sugar syrup, take it out. You see that a coating of sugar is available there. And it is something like a sugar coating you have, where it doesn't permit these particles to interact. Now, coming to synthesis, when you talk about synthesis of this nanomaterials or quantum materials, there are large number of methods available. These belong to two kinds known as bottom-up and top-down methods. The bottom-up method is a method where the material is built atom by atom. There is a method called molecular beam epitaxy, a method called molecular beam epitaxy, where the material is built layer by layer, atom by atom. And there is no new technology. It was available in 83, say about 40 years back, when I was a student of Madras IIT. You can build them atom by atom. This is known as a bottom-up approach. Whereas, if you try to take probably pepper and grind it in your mixie, all that you do is the blade goes and hits the peppercorns at a great speed. That peppercorn is broken to pieces. You get a pepper powder. And this is known as a top-down approach. You crush it. You go from top to down. It's called the top-down approach, crush it. Even today, people use the top-down approach. One method is called ball milling. The ball milling is not a very difficult thing for people to imagine. Assume that you have a good stainless steel dabba with you. Put about a handful of groundnut and put about half a dozen big sized marbles, goli kundu. Close the lid. Keep on moving it up down so that the balls collide with the walls of the container. And after 5 minutes, if you open, all that you find is that you have a powder of groundnut and not groundnut. This exactly is the thing that is happening in ball milling. You try to put steel balls or carbide balls, which will go hit against the material and crush it into powder. The basic problem in ball milling is it becomes contaminated and the size of the grains is very small. What do I mean by grains? You are very happy when you see that the maida that you are using, if you sift it through a mesh, you don't have any difficulties, it's good. But at the same time, if you grind rice or something else in your mixie and sift it through different kinds of sift, salad, if you try to use different kinds of salad, you will see that the grains are not the same. At different stages, different sizes are getting separated. And you see that the size distribution in ball milling is very poor. Not only that, the calcium carbide balls contaminate the material, and so the ball milling is not used if you are very particular about getting a particular size of these quantum materials. Then when it comes to chemical methods, you can do a lot of things like precipitation method is there, deposition is there, combustion is there. Then you can also do inert gas condensation. That is done when you don't want to get the material oxidized. There are cases when we are working with the materials, if you are working in the open atmosphere, the material can react with the air around it, atmosphere around it, and it can get oxidized. For example, let's look at the material with which we have worked, the copper sulfide. Copper sulfide is good. I work with it up to 400 degrees centigrade in open atmosphere. Nothing happens. It continues to remain as copper sulfide. But the moment I heat it at 600 degrees centigrade, the sulfur leaves copper sulfide and interacting with oxygen, I am now getting another material called copper oxide. You see that there are methods where the atmosphere really matters, and when the atmosphere really matters, we don't want oxygen to get in. People use what is known as the inert gas method, where you will be able to solve the problem. Sputtering is again a method where you build atom by atom. Sputtering is actually trying to melt it and then evaporate it and deposit. Electrodeposition is trying to deposit atom by atom and making it using electrochemical methods. Combustion, people easily understand. You can add appropriate fuel and combust. But there are, if each method has got its own advantage and disadvantage, then for materials which will undergo a sort of dissociation. If there are methods where dissociation is a problem, then people try to use what is known as laser ablation. People may ask me what is laser ablation. See, normally when you supply heat, what happens is heat is given to the material. Material as a whole has to melt, and then when you still raise the temperature, the material leaves the melt and you have a vapor in the atmosphere. Whereas when materials have a tendency to de-associate or dissociate, for example, when you take gallium arsenide, in gallium arsenide, if you melt gallium arsenide and keep it in the molten state for a good amount of time in open atmosphere, gallium will leave the gallium arsenide, making the gallium arsenide melt to be what we call as a non-stoichiometric thing, or for every arsenic atom, one gallium would have existed initially, but now the number of gallium atoms existing per arsenic would have come down. It may be something like for every 100 arsenic, only 90 gallium will be there and all that. For such things, people use a laser ablation technique. What is this laser ablation? You know that people can use kilowatt lasers. Lasers of very high energy. And I think most of you know that lasers have a very, very pointed, very small area light. Because of the very small area, the energy associated with the laser beam is so large that you will be able to melt a very, very small area of the bulk, and that immediately vaporizes. See, that's more important. It is an immediate vaporization that happens in laser ablation, so that laser ablation technique can be employed when materials show a tendency to dissociate and leave the material. Then you have things like spray conversion. For example, for making zinc oxide, we start with zinc chloride or zinc acetate, spray it in a hot atmosphere. When the spray jet is traveling along the hot line, the acetate dissociates and converts it to zinc oxide and deposits on as a zinc oxide film. There are other methods like the chemical methods. I'd like to mention 4 important methods called precipitation method, which is a very, very simple, cost-effective method. Then you can use what is known as whole gel method. I'll talk about it a little later. And you can use microwave assisted thing. And what is known as hydrothermal method. All these methods are useful. I'll talk about it little later. So when you want to use these materials, the first and foremost question that comes to our mind is, how do I characterize? I just told you about the laser ablation method, sputtering and all that, where there is a possibility that a molecule may not get deposited as a molecule. The stoichiometry or the ratio of the components will not remain constant. In which case, when you try to make a material, we want to ensure that the material formed is of a particular type. For example, let's look at the simplest thing which most of you know. It is possible to have copper and chlorine in these two formats. One is CuCl2, another is CuCl. People who still remember their higher secondary class, I'm excluding pre-university because people of my age would have retired by now, and I don't think anyone of my age is attending the lecture today. In the first case, copper is of valency 1 called cuprous. It's called cuprous chloride, and the other one is called cupric chloride. When I want to make a copper chloride, I want to know whether it is this type or this type that is formed. The best method will be to use X-ray diffraction. Go for X-ray diffraction. If you form a crystalline material, X-ray diffraction will tell you whether you have formed copper chloride, cupric chloride, or cuprous chloride, or whether a mixture of it. For example, when we made nickel sulfide, depending on the preparation methodology, we got about half a dozen variety of nickel sulfides, starting with divalent nickel, Ni2S2, normally we call it as NIS. You have a variety of things being formed. And to understand the band gap and other things, we go for UV visible absorption spectroscopy. If the absorption shows a behavior like this, let's say this is the wavelength and the absorption, when it shows this behavior, this is known as band edge, and we say that the band gap is given by this wavelength, or instead of this I can also put it as energy. Energy will be going in this direction, energy which is hc by lambda, it will be in this direction. You get the band gap. To measure the band gap, you can use UV visible absorption spectroscopy. If the material is luminescence, you can use photoluminescence spectroscopy, where you use shine light on the material. The light emitted by the material will be analyzed to understand the material. Yeah, again, using in XRD, not only the structure is known, people also try to use XRD to get the size. The interesting part is when you look at an XRD spectrum, it will be something like this. This will be 2 theta, and this is the intensity. And there is also a possibility that I can have another picture where this, I don't know whether people can appreciate the difference. In one case, you see that the band is quite large, whereas in this case, the band is very small. The band actually contains information on the size. When the band is very, very thin, or it is small and the band is wide, you see that a wide band would indicate that it is nanometric in size, smaller in size, and when the size grows, the size decreases. For this, there is a formula known as D by Scherrer formula. People can use the D by Scherrer formula, which relates the size to the half it at the angle theta, and you will be able to estimate. So size can be obtained through XRD, though there are other methods like dynamic light scattering and other things that you can use. Then you can use a scanning electron microscope. What do you want to use a scanning microscope? I can use a scanning electron microscope or a transparent electron microscope to again measure the size. In this case, the size will be actually seen by the user. You take a photograph of the material, and from the photograph you will be able to see the size. Not only that, that tells you whether the particles formed are in plate-like thing. It's something like plates being arranged one over the other. Or I have only spherical particles being formed. Or I have random sized particles, flower-like structures coming out, and all that. All these details can be obtained through a study of the electron microscopic image. And the surface is examined. This is used for examining the surface, how smooth or how rough it is. People use scanning microscope to understand what is the valency of the material. You use X-ray photoelectron spectroscopy. Thermal analysis is done. What is thermal analysis? We try to heat the material and look at the mass. What happens is, when you do that, it shows a behavior like this. You may be wondering why the mass is decreasing as you keep increasing the temperature. Let me say I prepare the material in water, or a material in water containing certain other organic solvents. What normally would happen is this water would enter the particles that are formed. It is not new to us. Let us ask a question as to why mustard, when it is dropped into hot oil, splits. The mustard dropped into hot oil splits. Water inside the mustard is trying to escape, and due to which it splits. In a similar manner, when there is water on the surface, it initially gets out, probably here, and at some other point also, water inside will get out. And as I told you, probably when I start with nickel sulfide and when I finally end at nickel oxide, it tells you when this happens. So I can find out where this happens using other tools and decide whether I should heat the material up to this point, or I can heat it only up to this point and leave it, because unless you do thermal analysis, it's very difficult to see whether my material will be stable, and otherwise, when it is magnetic in nature, people try to use vibrating sample magnetometer. One interesting thing which somehow I have not included in this list is the infrared spectroscopy. Most of you who belong to the science stream would know about infrared spectroscopy, which talks about the vibrational frequencies of the material which is available with us. When it gives you only the vibrational frequencies, people may ask me how this can be used to identify and understand the quantum behavior of the particle that is in hand. See, normally when you have large particles, the IR spectroscopy doesn't really recognize bulk and smaller particles. But when it comes to particles which are in the quantum region or the nanometer regime, you see that there is a possibility for the particle to be caught in a confinement. If the confinement is, say, about 5 to 100 nanometer, the vibrational frequencies of the species will be enormously increased because of this confinement. So if you have a material and if you see that the vibrational frequencies are increased, it indirectly indicates that the particle is under quantum confinement. That's very essential. You can use IR to identify whether there is any quantum confinement working with this material. Right. The next thing, sir, you said there are a lot of methods through which you can prepare materials. How do I go about choosing a method? That's a natural thing. How do I choose? Now, at least for the last 10-15 years, people have been shouting about using green methods and green technologies so that the humankind is not at a disadvantage. People want to make sure that there is very little waste and we don't consume a lot of energy in the process. And all these things together would add to what is known as a green technology. The first is waste to energy. You try to burn the landfill to generate electricity. People know that in Namakkal area, even chicken shit is used to produce uh, electricity. And I was told somewhere in Rajasthan, they use a community toilet for producing biogas. All the waste coming from the community toilet is collected and that is processed to get biogas. You can see that the night soil is used for biogas generation. And using electric transport, one can use electric cars, trucks, buses, scooters, and all that. But for electric transport, unless you use PV panels for charging, I do not agree with people that electric transport reduces pollution. If you use PV panels for charging the electric vehicles, yes, it really reduces pollution. Otherwise, if you generate it at some other point, for example, generate the power at Thoothukudi and use it at Trichy, you're not really reducing the pollution. The other interesting thing about electric cars, electric trucks, everything is that all of them today use only lithium batteries. And you know that lithium is the smallest kid in the metal family, the smallest metal, and it can cause enough and more trouble. And that's why the research is going on in trying to build sodium batteries and magnesium batteries, which are far more environment friendly than lithium batteries. And one can go for using preheated air or water, and these can be produced through solar thermal systems like solar water heater, solar air heater, and use it. And buildings should become self-sufficient. They can use solar panels on the roof for electricity. People can have large windows so that during daytime you don't need electricity to light the room. You know, today people talk about using DC fans, DC lights for the buildings because whatever electricity is generated through PV panel is stored in the battery can be directly put to use and not again sent through an inverter where the loss is about 20 to 30%. And you know, for quite long, Indians were very good that they never wasted power in drying of clothes. We used to have a large clothesline, put it in the open space and dry it. And I'll say Indians were more greenish in case of working with clothes and washing clothes. And you can reduce heat from roof using inverted parts. Again, construction should use low carbon. It's a very interesting thing. There was a man by name Baker who proposed that one should use only local materials for building. For example, if you are in Assam region where bamboo is available in plenty, people should use only bamboo-based buildings. Bamboo is used by them for reinforcement. When we are using steel for reinforcement, some of the Assamese use bamboo as a reinforcement for their buildings. And Baker proposes that you should not use the bricks that are burnt in a kiln, try to use the bricks without any heat treatment. Straight away, a mud block is used. It's not called a brick, you call it as a mud block. And try to use LED lighting. I can see that even a small village panchayat like Chinnadapatti, where I am living, has got only LED lights for the street lights. No more tube lights, no more CFLs. And you know, the another very interesting thing is people talk about vertical farming. You try to use trays, arrange one over the other, and try to grow plants. For example, kirai or the greens. You see that you will be able to use less land, less water, and it can be a more profitable venture. Composting, we should turn food waste into fertilizer. Using wave energy, you can use batteries. The problem comes here is how batteries get into green technology. The reason is simple. When you try to generate energy through non-conventional methods, we have a problem. Solar energy is not available during night time. Wind energy will fluctuate with the wind speed. So normally this energy is stored in a battery and used. And people are going towards batteries and energy storage devices, which are more environment friendly. You try to use green materials, local materials, renewable materials, etc. And what are all the things? If it follows all these things, then the methodology is known as green chemistry method, reduced toxicity. If you have a material which is soluble only in hydrochloric acid or nitric acid or sulfuric acid, try to find a material which is water soluble, so that after the reaction is over, we don't have any acidity in the residue, which is more toxic in nature. Try to start with starting materials which are less toxic. If you are working with a liquid-based production method, go for water as the solvent. When you use water as the solvent, you see that toxicity associated with the production of the nanoparticle is very much reduced, right? Try to use renewable sources. You can use renewable sources or methods that do not require large amount of energy. For example, I talked about precipitation method. It doesn't require any energy at all. Even a true temperature precipitation would occur. Then trying to design safe products. Biodegradable, whatever you get at the end, you should be able to get the byproduct and break it down, and you should be able to make the process biodegradable and environment friendly. Energy reduction is very essential. What do you mean by energy reduction? I'll give you a simple example. When people need crystals, to make a crystal of, let's say, 10 centimeter by 10 centimeter by 10 centimeter, a person needs to keep a furnace consuming about 4,000 watt for 72 hours. You know how much energy is spent. Whereas, if you try to use a method like microwave method, you set the microwave oven for 350 watts and use it for 5 minutes, you see that you use approximately 30 watt. You just imagine 400 kilowatt for crystals, and whereas with microwave method you use only 30 watt. Reduce the energy need, energy budget, and the process should be free from any accidents and shorter process. See, people talk about one part synthesis. At least with the female participants, the one part methodology may be very familiar. Occasionally, my wife used to say, I'll make a one part rasam or one part sambar. I used to wonder what is this one part sambar, one part rasam. It is a simple thing. She'll put all the ingredients, put them all into a cooker and then cook it. There's no need like the old methodology where you boil vegetables in this, then do step-by-step things. Finally, the process getting are coming to an end with your seasoning with the mustard and other things. There, the process involves 6, 7 steps. Whereas when she goes for a one-part rasam making, one-part rasam is made in just one step. It doesn't involve many things. So people look for shorter processes. It should not involve large number of steps. Instead of 7 steps, if you can do it in 2 steps, it is a green chemistry method. So what do we do? The first thing, everyone is trying to clean up and do things which is meaningless. And you see that most of the literature that is available is filled with toxic methodologies. Methodologies are now being revisited. People are trying to find new methods. And if the same product is obtained through some newer method, which is more profitable, you call it innovation. So innovative synthetic pathways are being found. People are trying to make it efficient. Going from inefficient, we want to make it efficient. Why you are interested in efficient? If I put A plus B and I get a C, the product is C, I should be able to get the maximum amount of C. If this is 1 gram and this is 1 gram, if I get 2 grams, that is the best methodology. But at least I should be able to get very close to 2 grams. Then it's one of the most efficient method. So that the product should be large or what you call as yield. The yield has to be maximized. And reagents are to be environment friendly. Industrial chemicals are to be used to the minimal extent. They should not cause any pollution to the atmosphere. For example, you start with something, as I told you about lithium. Lithium will escape and seep into the soil, thereby it spoils the soil. And organic chemicals, you can use it, but they can be depleted. Benefits, again, I told you, products won't cause toxicity. The most important thing, new products can be there. Renewable sources can be used, as I told you. For water splitting, you don't just use, today people talk about water splitting to get the hydrogen for hydrogen vehicles. That's a two-pronged approach. In water splitting, they try to use catalysts. These catalysts reduce the time taken or the yield is increased with the catalyst, and these catalysts can be used with renewable sources. You try to do the water splitting with the energy generated through photovoltaic panels and other things. Try to use renewable sources. Try to gain new insights into all these things. I think I'll just move beyond this. Yeah, this is what I told you. Atom economy is I should be able to maximize the product. Everywhere we are interested only in maximizing it. It is not like our trying to buy a jewel. You pay for 10 grams of a jewel, but finally you get 8 grams of a jewel. You see that 2 grams disappears into somewhere. And that is not what we need. In atom economy, if you give 10 grams, your jewel should be 10 grams. And catalysis, I told you the advantage of catalysis is in catalysts reduce the energy required for the reaction. They hasten the reaction. In some cases, the reaction temperature is drastically reduced. The production is enormously increased. You see that the activation energy is reduced. Therefore, you need less time. And reducing temperature, again, it is related to energy budget. The energy budget is reduced. And controlling site of reaction. Very interesting thing. How you do that? You can do that by appropriate methodology. If you are using a furnace, you see that if this is the dimension of a furnace, when you go from this side to this side, as you move towards the inner temperatures will be far lower than the sidewall temperatures, and you cannot control. There are methods by which you can control the temperature and site of the reaction. Degradation is needed. Right, now comes to quantum devices. Madam, do we need to give any small break? We have been going on for slightly over an hour. Shall we have a small break and continue, or we'll go on? Hello?
We can give a 5 minutes break, sir. Then we can.
Yeah, maybe we'll break for about 5 minutes and reassemble at, let's say, 11:50 or 11:55.
Okay, sir.
Yeah, at 11:50 we'll do that. Yeah, thank you. We'll have a
Sir,
small
5 minutes break. Yeah, a small.
yeah. Shall we start? Shall we continue?
Yes, sir, we can continue.
Yeah, we'll continue. Yeah. So we'll continue. The first device that I would like to talk about is the Josephson device called as a squid. We'll talk about squid in a minute. There is a device and an effect known as Josephson effect, where you have two superconductors separated by either a normal metal or by a insulator. When you do this, we have two things happening. One is you can have a current flowing or a current oscillating. And this was invented by a British physicist by the name Josephson in 1962, just a year after my birth. And the first one is known as DC Josephson effect, wherein it says that if you do not apply any electric field or if you do not connect a battery, even in the absence of a battery, a current would flow in the device. See, very, very interesting thing. Even without any external influence, no current or no potential to be applied externally, a current would flow. That is known as a DC Josephson junction. And if you apply a DC field, a DC potential, then you see that the current through the device will oscillate. And that is known as AC Josephson effect. In these two devices work basically on the principle of flux quantization. One important aspect about superconductivity is that if you have a superconducting ring and let's say a current I is flowing through it, the magnetic field produced in this coil, right, is quantized. The flux, if this is the area A, then the flux is given by B times A. The flux is quantized. That's very important. The flux is quantized, and a device that uses the flux quantization in superconducting rings is known as a squid, a superconducting quantum interference device. And this device is given by this structure. I have two paths. Through this path, a current flows. Through this, another current flows. And when you put a small magnetic field here, that alters the current through path A and B, and thereby an interference would occur. And use this for measuring extremely weak magnetic fields, such as 10 over minus 18 Tesla. You see that it's a very, very small field. Even the electric field due to single electrons can be measured. It is such a beautiful device, a squid. This is a quantum device. It uses quantum interference or the interference of the oscillating currents through the two paths, which I showed you two paths. The current through this is oscillating, current through this is oscillating. I am sending a current, I told you. There is an external field. So current through this is oscillating, this is oscillating. When you impress a field here, you see that this field will alter the oscillations, and thereby, due to the addition of the two currents, you have interference. Interference is addition, and you have magnetic field measurement using squid. The other thing is spintronics. In many of the measurements, people use either the electronic energies, vibrational energies, and all that. The spintronics is the one where the spin energy is utilized. Whenever we talk of spin, we say that spin can be either upward or downward, you know that these two spins have their own energy. They are separated by an amount of energy, and if you can work with this spin energy, then you call it as spintronics. What people do is they try to align the spins and then work with it. Using spintronics, people are trying to make even single electron transistors and so on. In fact, it is spintronics that is expected to provide a great breakthrough in trying to fabricate the quantum computers or quantum devices. So the other thing that you need is for quantum devices that use quantum mechanics is what we have seen. Devices that use quantum materials. I take one strong example, namely a energy storage material, storage part, because people are so much bothered about energy storage material. I told you photovoltaic panels, the energy is not constant because due to overcast sky, passing cloud and all that, the energy output changes during night time. Solar panels are useless. So we always need to store it because I should be able to supply energy when it is needed the most. So we try to use batteries for storing the generated energy, and identifying the right kind of storage material is equally important. You may ask me, sir, already there are batteries, rechargeable batteries available, like the lead acid battery, nickel cadmium battery, the iron batteries, lithium batteries, and so on. Why do we need some other energy storage device? I think people are well aware that in most of our household inverters, we are using lead acid batteries, which are rated at 12 volt and 150 ampere. That means I can have 12 into 150, 1800 watt in 1 hour. Or I can take 180 watts for 180 watt for 10 hours and so on. But these batteries cannot be charged at a very fast rate. Probably you can charge it at 1/4, say about 40 ampere hour. It takes 4 hours to charge the battery. If we try to charge it at higher speeds, the electrodes in the lead acid battery, they go bad. When the electrodes go bad, you see that it's difficult to use the battery, it goes waste. And in all these, electrochemical energy is stored and we try to use it. But there is another category called regenerative power in automobiles. What is regenerative power in electric automobiles? In electric automobiles, when you are ordinary automobiles, when you brake, the energy of motion is converted to heat on the brake pads and on the hub. Therefore, it generates enormous heat in the braking region. But at the same time, if this braking energy can be converted to electricity, we call it regenerative power. In electric automobiles, the motor which runs the automobile becomes a generator when someone presses the brake pedal. The moment you press the brake pedal, the motor becomes a generator. Large amount of power is produced. But now comes the question. Large amount of power is produced, but in how much time? Is it produced in 1 hour? Is it produced in 10 minutes? 5 minutes? No, it is produced only in about 5 to 6 seconds. large amount of energy is produced in very short time, that means that energy cannot be stored by these lead acid batteries. They are incapable of storing it because I cannot supply the charge to lead acid battery at that faster rate. So I need a device which can take up the energy at a faster rate. What is the device that can take up the energy at a faster rate? Most of you who have studied it in higher secondary level will know that capacitors can do it. A capacitor can be charged in microseconds or even nanoseconds, very fast. But we have a problem. The capacitor cannot hold large amount of energy. Now we are with two extremes. One device which can be charged at a very fast rate but cannot hold enough energy. Another device which can hold the enormous amount of energy, namely the battery, but cannot supply or receive energy at a faster rate. Is there anything that acts as a via media for between these two? Yes, there is one that is known as a super capacitor, which we'll discuss in another uh, 5 minutes. Basic principle of battery. All that you do is when there is no load, you supply current, the electrolyte is charged. And when you are connecting a load, the charges move, electrons move towards the anode, and right, then you see that the other charges move, you complete the section. And in case of capacitors, this is the air capacitor between two plates. Air is there, you can charge it. The charging energy stored is quite small. Energy stored is given by half CV square, right? You may charge it to 110 volts, so it is 100, and capacity is, let's say, about 1 microfarad. You store 10 over minus 4 or less than a millijoule. It's useless. What people do is they try to fill this area with an electrolyte, so it becomes an electrolytic capacitor. It is improved, but what we do is we go for a next category called electric double layer, right? Wherein I have one metal plate on which a carbon material is coated. I have another material on which again carbon material is coated. And these two are separated by a separator which contains ions. And when you charge it, ions from this will move and there will be electric polarization at the interface between this electrolyte and this material. This electrolyte and this material, you see that because of large polarization, the electric double layer will give you capacities are in the range of farads or hundreds of farads. Large capacity is obtained. These are known as electric double layer capacitor. It again works on the principle of polarization. But we are not very happy with it because the carbon that people are using here are the nano carbon materials. You don't use bulk carbon because nano carbon has got large surface area. They are very useful for this purpose. Okay, yeah. So we have super capacitor. Capacity is very large, thousands of farad per gram, right? And very fast power delivery. So what people do is they try to use it whenever power is available at a smaller duration, or when you need large power in a short duration. For example, when you are trying to accelerate your vehicle from rest. For example, in a signal, if you are staying from the signal, when you are trying to accelerate, you always go to the first gear because at the first gear, the power delivery is very large. The torque generated is large and do it. Similarly, what they do in electric automobiles or what is known as hybrid automobiles is they use both petroleum product and also the super capacitors wherein the supercapacitor will again be activating, and you see that along with the fossil fuel, the power delivered by the supercapacitor will drive another motor so that you can accelerate at a faster pace. Or whenever you have problems like what is known as a load leveling problem. Suddenly, when the load goes up, the battery will buck. Buck means the battery output will come down and the system will fail to perform. I repeat, there is a case where there is a pulsed power. During pulsed power, if the power supply is not good, what will happen is suddenly the machine will stop functioning. In order to avoid this, what we do is we use a methodology called load leveling. For load leveling, the supercapacitors are used because they can deliver power. I'm not sure whether people know if there are any electrical engineers in the participant group. You'll see that normally in many of the power supplies, there will be 1,000 microfarad capacitor connected along with a 10 PF also will be connected. Has someone noticed such a thing in any circuit? Along with a very large capacity, a 10 PF is connected. When you see such things, we get little worried. When you add them 1,000 to 1,000 microfarad, if you add 10 PF, it doesn't really improve it, but you'll see that the 1,000 microfarad cannot respond to changes faster, whereas this will respond. If there are any pulses, the pulses will go through this and the power supply will be better. In a similar manner, along with a battery, people connect a supercapacitor. So when this cannot supply current in a short interval, supercapacitor will deliver it at a faster. So like what we do in Tamil, it acts as a tol gudukkum. Right? This is exactly what you have. Two types are available, double layer and pseudo capacitor. I'll concentrate mostly on pseudo capacitor because these are based on nanomaterials. So what happens here? I have a material, then same thing. It is something like a sandwich. I think I have the sandwich structure. Yeah, this is a sandwich structure, a current collector, the active material, a separator, I should say separator come reservoir, and again the material and this. What happens is electrode material would store energy. And the electrode material is chosen such that the electrode material can undergo this oxidation and reduction reactions. That means you will be able to store charges into it and retrieve charges from it. Right? If you are putting electrons, you call it oxidation. You are trying to do the other way around. You have reduction or adding and removing things. So on one side, if you say that negative charges are sent this way, positive charges will come this way, they get attached to this. They are not attaching. There are two processes happening here, both absorption and diffusion. Absorption, as I was telling you at the start of the lecture, is a surface phenomena, whereas diffusion is a bulk phenomenon. Please do not get confused with the bulk which I used at the start of the lecture and now. Bulk means if you have a particle, this is what I would call as a bulk. So what happens is in diffusion, the charges get into the material and stay there. Right? So you have oxidation reduction reactions. Together, these are known as Faradic processes. Right? So I use a separator, but the separator is meant to separate charges, but the separator contains lot of electrolyte so that the separator acts as the reservoir of charges as well. Charges are stored in the reservoir so that charges of one type move towards the left, charges of the another type move to the right, and you have charge storage. And capacity is obtained through this. You try to find out what is the charge that you have loaded, what is the potential to which it has been charged, you get the capacity, simple thing. We try to use what is known as a charge discharge method. It's called the galvanic charge discharge. When you do this charge discharge at a constant current, it is charged. At a constant current, if we charge it for t moments, it is this divided by V, right? I get the capacity. A very simple way of calculating the capacity of a supercapacitor. I think I'll skip this slide. Yeah. The other thing is the electric double layer capacitor is one thing that probably you'll be interested in because they were one of the first to come and commercialize. They use the carbon materials like carbon dots, the graphite layers. They use the carbon nanotubes and exfoliated things, reduce graphene oxide and all that for making this. And this is a case where we do not have charge storage by means of movement of charges. There is no movement of charges, no diffusion, but here I have polarization happening at the thin electrode-electrolyte interface. The interface width is of the order of nanometer to micrometer. You see that in such a very thin layer called interface, the imaginary plane at which the electrode and the electrolyte meet, that is known as the interface. At that surface, the surface thickness is so small, you will be able to store large amount of charges and no physical change happenings. And importantly, it can sustain millions of cycles. Unlike our lithium batteries today, the lithium battery first 3 months performs exceedingly well. Charge it in the morning, up to next morning, at least 30% of the charge remains. But after 6 months, you see that morning you charge it, again evening you have to charge the battery and all that. You see that they don't last even 1000 cycles in the real value. It's a problem. But if you try to use EDLCs, the electric double layer capacitors, they can sustain millions of cycles. You don't keep spending on the battery, and this is good. And because of the nanometric thing, they have small pores. What do you mean by pores? If I have materials, what really happens is if they are so closely arranged, you see that there is no space. But if the materials are arranged this area is what you call as a void or a pore. When there are pores, my electrolyte will be able to get into this region and attack all these particles. And so you see that I need pores and large surface area, which are very good for the performance of these electric double layer capacitors. It is so with the other kind called pseudo capacitor. So as I told you, mostly it uses carbon nanotubes, graphene, and other things. When you charge it, it gives you an ideal capacitor thing, a rectangular curve. If you have the current and voltage, it will be something like this. Right? The structure will be more rectangular in nature. You can see that this approximates to a rectangular behavior. When it comes to pseudo capacitor, I told you it was redox reactions. There is a physical change, and they undergo, I mean, they don't last millions of cycles, at least they last 10 to 20,000 cycles. In our laboratory, we made pseudo capacitor which could last 10,000 cycles with 10% degradation. The degradation was very, very small, and they can store energies comparable to batteries. People are trying with a material called ruthenium oxide, highly studied and all that, very efficient, but it is not that abundant on Mother Earth, and it is also known to be a toxic metal, and so people were looking for alternates to ruthenium. As alternates, manganese, nickel, cobalt have been tried. Some of the conducting polymers, I shouldn't say polymers, they are conducting polymers, have been tried. Now comes a question. Let me see whether I have it in the next slide. No. Yeah. And these things show redox peaks. What is that? It's a simple thing. When you try to do what is known as cyclic voltammetry, increase the potential slowly and measure the current, you see such peaks. These peaks indicate that at those points, oxidation is happening or reduction is happening. And these peaks are characteristics. When there is only one peak like this in this picture, you say that there is one reduction reaction taking place. There are cases where we have seen, you see that there are more than one peak. This happens with materials because of their quality. And the most important thing is, even today, people are concentrating more on transition metals. I think people know what is transition metal. They are also known as iron group metals. If people remember the D block elements or the iron group elements, what is their speciality? Let me know. Put the names: copper, cobalt, nickel, chromium, iron, manganese, there are vanadium. What is special about them? If you see, if you are looking at silver, gold, or sodium, or potassium, they have only one valency. They are monovalent. On a K plus ion, you can store only one electron, nothing beyond that. Whereas you come to these things, I just mentioned some time back to you that the copper can exist in two valencies, namely copper plus and copper 2 plus. Copper plus is known as cuprous ion and copper 2 plus is known as cupric ion. Similarly, cobalt can exist in 2 plus and 3 plus. Nickel can exist in 2 plus and 3 plus. Iron can exist in 2 plus and 3 plus, where we call it as ferrous and ferric. Chromium can exist from 3 plus to 6 plus. Vanadium can exist in different valencies. Because they can exist in different valencies, you see that if I use potassium, probably I can store one charge. When I try to use chromium, I can store almost 4 charges. For example, if I'm using copper, you'll see that if I use divalent copper, I can convert from copper 2 plus to copper plus to copper metal. That means for every copper ion I have, 2 charges can be stored. That means the charge storage is very large when you try to use these transition metals. As I told you earlier, due to cost and non-eco-friendly nature, ruthenium oxide has been substituted. People have been using sulfides as well. Probably in this lecture, I'll talk about the sulfides to some extent. As I told you, nanomaterials are preferred mainly due to their porous structure and large surface area. Right. Now comes a question. Why I use this? I told you, depending on how you prepare the material, I can get more than one phase. Look at it. Nickel sulfide. I start only with nickel nitrate and thiourea. There are two things, right? Nickel plus, depending on the temperature at which I make it, depending on the relative ratio between nickel nitrate and thiourea, a variety of nickel sulfides can be formed. I can form Na3S2. I can form Na3S2 with a small non-stoichiometry. I can form Na6S5. I can form Na3S4, NIS. You see that each of them have their own merits, B merits and all that. And in our case, we could make nickel sulfide in what is known as the millerite form, and in another hexagonal structure also. You see that nickel sulfide performed very well. We could get excellent capacity through that. Right. Coming to the preparation methods, I have precipitation method. But is it good? Yes, because room temperature synthesis. You don't heat it. You don't spend energy on preparation. And yield is more than 90% yield. Excellent. I told you atom efficiency, more than 90% yield. Almost 99% yield is available with precipitation. But what is the problem? For most of the things, we expect size to be uniform. In precipitation method, you don't have any control over the size of the particles formed. And so, if you are very particular about the size being uniform, the precipitation method is ruled out. You can use sol gel method. Good. It's again a room temperature method, but particle size are very small and the yield is the villain. You get very little yield, about 10%, because it is something like you are trying to make this, what is that, rava payasam, and trying to embed mundiri parpu into it. You know that the quantum of cashew nuts you put into that payasam will be very small, right? And you see that you cannot get a large yield. There is a hydrothermal method which is again good. You do it at around 150 degrees centigrade for a shorter duration. It is good again. And there is a danger that due to large pressure there can be explosions. There is another method called microwave assisted method, which is very good. See, because in these two things and all that, we never are bothered. When you heat, if I have an area like this, are they heated uniformly is a major question. In the case of microwave, I'm not sure whether people have ever, the participants have ever tried to cook poppets using microwave oven. If you haven't tried, please try it today. Use a poppet, set your microwave for about 80% power and fix it for about 30-second duration, and take it out and see after 30 seconds, almost uniformly everywhere the papadam would have been heated up. You see that there is uniform heating. Then we say that uniformly nuclei are formed. uniform nuclei formation, and I have size, what you call as a single size. I should tell you, in our laboratory, where in Gandhigram we don't have great sophisticated machinery, we have used microwave oven meant for home use, right? And in 5 minutes, I told you start with, if you use crystal growth and all that, you will spend a lot of power. We used a microwave oven at 350 watt and used it only for 5 minutes. You know that it is 350 into 112, it is 30 watt. With 30 watt of power, we will get excellent nickel oxide material. You see that one of the most things. So depending on what you need, you should be able to select a methodology whereby you want to make a quantum material or a nanostructured material, and all these routes are green chemistry routes. One can select them depending on the need. If my application requires a single size, yes, I should go for microwave method. If my application is not very particular about the size, go for precipitation, because this is far more greener than the microwave assisted method. I think probably I'll stop here because all people are people with enormous experience, and sitting through a lecture for 2 hours plus is essentially a very difficult thing. If people are interested, I'll tell you how to make the measurement of capacity. Maybe I'll spend another 5-10 minutes and wind up. Else I can stop at this point. And also we are going towards lunch. Madam?
Sir, very good afternoon, sir. I have a question on green computing, sir. How green computing differ from traditional computing? Can you provide any real life example so it will be easy for us?
No,
Sorry,
real
green
life
chemistry.
example does not say the
Yeah, yes, sir.
basic problem is whatever green technologies we talk of systems wherein the assault on the environment is reduced. If you look at it in green computing, we should go for power supplies which are green. For example, today we are using lithium batteries, and slowly lithium batteries are to be replaced with the supercapacitors that I have been talking about. These supercapacitors have two advantages. I'm using nickel oxide or ruthenium oxide and all these things. They are not that environment unfriendly, and they don't require any maintenance as the lithium batteries are. Unlike lithium, they do not pollute the environment. Then when you are using the computers, you remember some 10 years back, people were using huge cathode ray tube monitors. But today, no one uses cathode ray tube monitors because they generate a lot of heat, thereby causing heat pollution on the environment. People have gone for LED structures. Now, people are not happy with just the back illuminated LED of the olden days, where they used the CFLs for back illumination, but today you have tiny LEDs in the back plane which illuminate the LCD screen. So people talk about LED screens, they are essentially LCD screens with backlighting with LED. And in all these cases, we want to do the computing at lower potential and at lower current. When you do that, you have it. Today most of the computers work at 3 volt and not at 5 volt. Because when you're working at a lower potential, the current drawn is smaller and the heat emanated. I remember one Sony laptop which I had. If I try to use that for 15 minutes, put it on my lap and work as a laptop, my thigh will be burnt. But today you use a good laptop, even for 2-3 hours on your lap, it's not getting heated up. That's because of the green concerns that people have shown. So again, the approach is towards reducing the power consumption, reduce the power need, and trying to reduce the number of components required. Today, most of the computers do not use additional devices outside the thing. There is only one device which does the processing of audio, video, game, everything. Most of the things are integrated into a single chip. By doing such integration, they reduce the even space needed for your computer. In fact, today you can buy a good computer size of your notebook. Only thing is, yes.
Thank you so much. It was very
Thank
clear.
you.
I able to understand.
Good afternoon, sir.
Good afternoon.
Excellent presentation, sir.
Yeah. Thank you,
Okay.
madam.
Sir, my question is for squared devices, sir. So what type of measurements are in squared devices particularly useful for, sir?
Which device, madam, please?
What type of measurements for squared devices particularly useful for, sir?
No, see, actually, every measurement depends on what for your using. For example, in my case, I am working on supercapacitors. What we do is we use two kinds of charging methodologies. One is called as cyclic voltammetry, where we slowly increase the voltage and measure the current. I showed you a graph. Hope you remember the graph. I'll try to get it. Yeah, this particular thing. You see that the area under this curve will continue twice the amount of charges I have put. All that we do is this current and this potential, we find out the area. Area gives me a measure of the capacity. The other thing is I can go for what is known as charge discharge. I'll try to get a charge discharge thing. For want of time, I have not done that. Yeah, this is the charge discharge curve. You can charge it at a constant rate. If you are charging it, let's say, for example, 150 seconds, then the charge enclosed is I times T. You can say the charge I have provided is I times T, and the voltage to which this charge is V, because you know that the capacity is Q by V. This is what I have. And because here we always measure the specific capacity, it will be divided by the mass of material used. So we call it as I times T divided by V divided by M, so that we get the specific capacity in farads per gram.
Okay, sir. Another one question, sir. What is the difference between DC and RF squared, sir?
DC and RF split. See, that depends on the potential, the kind of frequencies which we are working. When I'm working with a DC split, as I told you, you don't need to apply an external potential. Whereas when you go to this, the potential applied is adjusted such that the frequencies are in the RF region. The reason why they choose RF region is that RF frequencies can be easily picked up by a pickup coil.
Thank you, sir.
That's exactly the mechanism through which NMR, the nuclear magnetic resonance, is happening. In that, they use radio frequency, and the amount of energy absorbed from the RF is measured. In this case, we try to find out the frequency. Shift in frequency gives you the measure of the magnetic field.
Okay, sir. Thank you, sir.
Sir, good afternoon, sir.
Good afternoon.
It was excellent, sir.
Thank you, sir.
Sir, my question is,
Breaking of the voice.
and also possible to implement Hamilton algorithm in quantum computing.
I think it should be, sir, because the basic problem, as I told you, is though people have been talking about quantum computing for more than 2 decades, not even half a dozen devices have been made. Still, people have made only very few AND gates and other things, and you don't see that not even a single 2-bit adder could be realized. The realizing all these things is a major thing. Probably if people are able to find out and obtain things wherein you will be able to use syntronics at near room temperature, things will become possible. The other thing is again costly way of doing.
Okay, sir. Sweetly with sir. Thank you.
Okay, Dhanush sir, unmute and you can speak.
Yes, sir. Dear Murali sir, thank you very much for excellent presentation on this 6 days online FDP. And I take immense pleasure in delivering the vote of thanks. Myself, Dr. C. Dhanush, Assistant Professor of Chemistry from Rathinam College of Arts and Science, and a proud alumni of the Gandhigram Rural Institute.
Oh, nice.
And I primarily thank our CEO, Principal, Vice Principal, and Dean R&D for the support and approval to conduct this online FDP on quantum computing. Next, I wholeheartedly thank the head of computer science, Dr. S. Raja, and Dr. T. Velmani, and head physics, Ms. D. Umamageshwari ma'am, for organizing this FDP and took a lot of pain in delivering the deliverables of quantum computing. And I especially thank the chief resource person of today's event, Dr. G. Muralidharan, Professor of Physics, Gandhigram Rural Institute, for his patience, knowledge sharing, valuable time, and clear-cut explanation on quantum domain and other parameters of quantum. And finally, I thank the department faculty members, participants, and other people who worked hard for the successful completion of this FDP today. Thank you all. Thank you very much for your time and day, sir. Stay connected, sir. Thank you.
Thank you so much. Thank you. Shall I close it?
Yes, sir. Any?
So nango in gate pakata illi idar dining.